Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Sciences, SOS, Master's Degree Programs, Master of Science, Analytical Chemistry, MSCANCHEM, Semester I, MCHL-012 Chemistry Lab 2, Part A Identification of Components in A2 Component Mixture and Preparation of their Derivatives. Unit 1 Basic Principles of Separation and Identification of Organic Compounds. 1.1 Introduction. In your practical classes in B.Sc, you must have done the identification of organic compounds under the qualitative analysis of organic compounds. But here, we will further move ahead in this journey and you will study about the separation of organic compounds in Part A of the course when present in a binary mixture and their identification, although according to their physical state, in a binary mixture, i.e., which two components or compounds are present, the two compounds either be both solid or both can be liquids or one is solid and the other can be a liquid. In order to keep the things simple, in this lab course, you will be provided only with the solid-solid type mixture of organic compounds in the laboratory. Expected learning outcomes. After studying the contents of this unit, you should be able to explain the general principle of separation of organic compounds from their mixture, carry out such separation of components of the mixture after ascertaining their nature as acidic, basic or neutral, characterize the functional groups present in the separated compounds by performing their characteristic tests, and identify the separated compounds using their physical constants and prepare their suitable derivatives. 1.2 Principle. You know that the separation of a mixture of two organic compounds can be done using a number of methods. For example, chromatographic methods and solvent extraction method are used for such separation. Here, we will be using mainly the solvent extraction method. You are also familiar with this method of extraction from your earlier studies where you might have extracted the products of a reaction using an organic compound. Say X can be extracted from aqueous medium by using the organic solvents such as diethyl ether, dichloromethane, ethyl acetate, etc. The distribution of the compound X between organic and aqueous layers is given by the distribution coefficient or the partition coefficient which is given below. K is equal to Cong.X in organic solvent upon Cong.X in aqueous medium, water. Thus, an organic compound having large K value will facilitate the extraction of the compound in the organic layer. Also, when we have to separate two organic compounds, we take advantage of their acidic basic properties, i.e. their chemical nature, and convert these acidic basic compounds to their salts which are water-soluble. Hence, an acidic basic compound can be separated from a neutral compound when present in a mixture by using solvent extraction or liquid-liquid extraction. 1.3 General methodology. The general scheme of this separation can be represented as follows. Look at the screen. After that, the two pure compounds obtained from the mixture are separately analyzed by following the usual scheme of identification of organic compounds. Similarly, we can draw a flow chart for the separation of A basic, BH, and A neutral compound Y, soluble in an organic solvent plus BH, extraction with 2MHCl2 chloride salt, soluble in water. Y can then be extracted using an organic solvent and B is separated in the form of its salt in the aqueous layer. The two layers can then be separated using a separatory funnel. Pure Y can be obtained by removal of the organic solvent. Pure BH can be recovered by treating the chloride salt by making the solution basic and then extracting BH from aqueous media by using an organic solvent followed by removal of the solvent. Here also, the two compounds Y and BH are separately identified using the usual scheme of the identification of organic compounds. The usual steps involved in such an identification of separated individual compounds from the mixture are as follows. Steps involved in identification of separated individual compounds. Look at the screen. 1.4 Some procedures involved and correlating the observations with identification. Here, we will discuss the steps listed in Sec 1.3 in more detail and the information derived about the compound after performing these steps. You will be recording these details in your practical notebook. 1.4.1 Physical examination. A. Physical state. Observe whether the compound is solid or liquid. As generally, you may be provided with a mixture of solid compounds, therefore, the separated compounds will be solids. So, you have to look for its nature as crystalline or amorphous. B. Color. The color of the compound may indicate some likely classes as follows. I. If a compound is colorless, it may be an aldehyde or a ketone. An alcohol, an ester, a carboxylic acid or an ester. Carbohydrates are also colorless and so are the simple hydrocarbons. 2. Some compounds, which are actually colorless, turn into pinkish or reddish color due to slow oxidation by air. The examples of such compounds being amines and phenols, etc. 3. Some typical yellow-colored compounds being iodoform, nitro compounds, quinones, etc. However, p-nitroso compounds are greenish, yellow is color. 4. Compounds having red-orange color are azo compounds, naphthaquinones, etc. C. Odor. Odor of a compound sometimes gives an important indication about its nature. You know that esters have fruity smell and alcohols and chloroform are also sweet smelling. Acetic acid smells like vinegar and the odor of cinnamaldehyde is like that of cinnamon. Benzaldehyde has an odor, like bitter almonds, and phenols have a typical phenolic odor. Some aldehydes, carboxylic acids, and acid halides have pungent odor while amines have fish-like smell. D. Flame test, also known as ignition test, involves heating a small amount of the compound on a nickel spatula over a low flame. The color of the flame and the odor, if any, is observed, which indicates the following. Look at the screen. 1.4.2 Elemental analysis. The elements carbon, hydrogen, and oxygen are assumed to be present in an organic compound. But the presence of elements nitrogen, sulfur, and halogens can be checked by first converting them into ionizable inorganic substances, which can then be determined by the methods of qualitative inorganic analysis. For this purpose, Lassen's test is very commonly used in the laboratory. Lassen's test, the organic compound on fusion with metallic sodium yields the following sodium salts: NaCN NaCN, to Na-S Na2S, Na-X Na-X, X is equal to Ci, Br or I, NaCNS NiCN. The test is performed by first preparing the Lassen's extract. A clean dry small piece of sodium metal is taken in an ignition tube and the ignition tube is slowly heated to melt the sodium. A small quantity of the compound, 15 to 20 milligrams, or a drop or two of the liquid sample, is added to the ignition tube after removing it from the flame. The ignition tube is then heated again slowly so that the compound reacts with sodium. The ignition tube is then strongly heated for about a minute or so, and then it is plunged into a china dish containing about 10 ml of distilled water. The procedure is repeated with one or two more ignition tubes. The contents of the china dish are boiled for 2 to 3 minutes and then filtered. The filtrate or the Lassen's extract is then tested for the extra elements as explained below. A. Test for nitrogen. To a portion of the Lassen's extract, I about 1 ml taken in a test tube, solid ferrous sulfate, about 50 milligrams, is added. A dark greenish-gray precipitate of ferrous hydroxide so obtained is heated for a few seconds. Ferrous sulfate reacts with sodium cyanide to sodium ferrocyanide, FeSO4 NaCN, Na, FeCN, Na2SO4, sodium ferrocyanide. The heating results in the oxidation of some ferrous ions to ferric ions. The contents are then acidified using 3 to 4 ml of dilute sulfuric acid. The sodium ferrocyanide then reacts with ferric sulfate to give a precipitate of ferric ferrocyanide, which is blue in color and is called Prussian blue. 3 Na, Fe, Cn, 6 to Fe2, so 4, 3 Fe 4, Fe, Cn, 6, 3 6 Na to So 4. B. Tests for sulfur, Prussian blue. I. Lead acetate test. Another portion of the lessons extract, I about 1 ml, taken in a test tube is acidified with acetic acid, 2 ml, and a few drops, 4 to 5 drops, of lead acetate solution are added. The appearance of a black precipitate of lead sulfide indicates the presence of sulfur in the compound. Na S, CH, Cu, PbPbS to CH, COO Na, black. 2. Sodium nitroprusside test. To another portion of the sodium extract, 1 ml, 1 to 2 drops of a freshly prepared aqueous solution of sodium nitroprusside are added. The presence of sulfur is indicated by the appearance of a deep reddish-violet color. Na, S Na, Fe, Cn, No, sodium, nitroprusside, Na, Fe, Cn, numbers, sodium, sulfonitroprusside, reddish-violet. C. Test for nitrogen and sulfur present together. I. Test with FeCl3. About 1 ml of sodium extract is taken in a test tube and is acidified using 5 to 6 drops of dilute hydrochloric acid. It is then treated with 2 to 3 drops of ferric chloride solution. The presence of nitrogen and sulfur is indicated by the appearance of a blood red color. 3 Nicene FeCl Fe, SCN, 3 NaCl, ferric, thiocyanate, blood red. Note 1. If the organic containing both nitrogen and sulfur is fused with an excess of sodium for the preparation of lacins extract, sodium cyanide and sodium sulfide are formed instead of sodium thiocyanate, and the test for NaCN and Na2S can be performed. NiCN to Na, NaCN, Na2S. D. Tests for halogens. Note 1. I. Bilstein test. Heat a copper wire having a small loop at its end in a flame until the flame is no longer colored. Cool, dip the loop in the organic compound and heat on the edge of a clear flame. A green-colored flame indicates the presence of a halogen. Fluorine does not respond to this test. This test is extremely sensitive since minute traces of halogen-containing impurities give this test. This test may also fail for very volatile liquids, since they evaporate before the copper wire is heated sufficiently to cause decomposition of the given compound. 2. It is also to be noted that certain compounds not containing halogen, example, derivatives of quinoline, pyridine, organic acids, and urea, may also impart a green color to the flame. 2. Silver nitrate test. Procedure. Acidify the sodium extract, 1 ml, with dilute nitric acid, 2 to 3 ml. Boil the solution gently for 1 to 2 minutes to expel any hydrogen cyanide or hydrogen sulfide that may be present due to the presence of nitrogen or sulfur in the organic compound. Add silver nitrate solution 0.5 ml to the above solution. A white precipitate readily soluble in ammonium hydroxide indicates the presence of bromine. In case of a yellow precipitate insoluble in ammonia solution is formed, the presence of iodine is indicated. See note to below. Nix AgNO3 AgX Nano 3. Note 1. If the given compound does not contain N or S as extra elements, the extract need not be boiled with nitric acid. 2. The color of the silver halides and their solubility in ammonia solution are not dependable observations for inferring the presence of specific halogen, Cl, Br, I, in an organic compound because the amount of sodium halide formed by fusion of the organic compound with sodium is very small. Even silver iodide, which is present in very small amounts, will be soluble in excess of ammonia solution. Thus, a positive silver nitrate test will only indicates the presence of a halogen. To find out which halogen is present, the layer test should be performed. 3. Layer test. When the presence of a halogen is indicated in the compound by silver nitrate test, to identify the halogen, the layer is performed. Here, the sodium halide formed in the lacins extract gets oxidized to the corresponding halogen, which gives a characteristic color on dissolving in the organic solvent. For example, if the bromine is present as the halogen in the compound, then oxidation, of Nabia formed in the lacins extract will give bromine gas, which will dissolve in the organic solvent to give an orange-brown color. However, if the organic compound contains iodine as the halogen, then the Ni formed in the lacins extract on oxidation will give I2, which on dissolving in the organic solvent will give violet-purple color. Procedure: take about 2 ml of sodium extract in a test tube and add 1 ml of concentrated nitric acid to it. Heat the test tube for about half a minute. Add 1 ml of chloroform or carbon tetrachloride to the test tube and shake the contents well. Observe the color of the organic layer. If it is violet-purple in color, the presence of iodine in the compound is indicated. If it is yellow-orange in color, the presence of bromine in the compound is indicated. If the organic layer is colorless and the presence of chlorine in the organic compound is indicated as the silver nitrate test for the presence of halogens was positive. 1.4.3 Solubility behavior. The solubility of the compound in water, ether, NiCO3, 5% NaOH, DIL.HCl, and Cong. H2SO4 can give some indication about its nature as summarized in the Table 1.1 given below. Table 1.1, Solubility of different classes of organic compounds, Group I, soluble in both ether and water. The lower members of the homologous series of alcohols, phenols, aldehydes, ketones, acids, esters, anhydrides, amines, nitriles, Group II, soluble in water but insoluble in ether, polyhydroxy acids, glycols, polyhydric alcohols, polyhydroxyaldehydes, and ketones, some amides, sulfonic acids, Group III, soluble in 5% sodium, hydroxide solution acids, phenols, some primary and secondary nitro compounds, oximes, Group IV, soluble in 5%, hydrochloric acid primary amines, secondary. Aliphatic and aryl alkyl amines, aliphatic and some aryl alkyl tertiary amines, Group V, not containing N or S, 1, soluble only in Cong, sulfuric acid unsaturated hydrocarbons, some polyalkylated aromatic hydrocarbons. Alcohols, aldehydes, ketones, esters, anhydrides, Group 6, not containing N or S, 2, insoluble in Cong, sulfuric acid saturated aliphatic hydrocarbons, aromatic hydrocarbons, Group 7, containing N or S, compounds not in Groups I to 4 nitro compounds, tertiary, amides, nitriles. 1.4.4 Determination of physical constants, I. Melting point. The melting point of the compound is determined by using the Kjeldahl method. This procedure used is known to you from your earlier lab courses. 2. Boiling point. Although this time we are giving you a mixture of solid compounds, therefore, determination of boiling point is not relevant here, but in case, you have to identify the separated unknown compound. Its boiling point can be determined either by distillation, if the quantity is quite sufficient, otherwise, the microscale method, i.e. the Savolobov's method is used to determine the boiling point of the liquid compound. The procedure for the same is already known to you from your lab courses in the earlier classes. 1.4.5 Functional group identification. Depending upon the extra elements, i.e. nitrogen, halogens, etc. present in the compound, the tests are to be performed on the compound for the following classes. In case no extra element is detected, the compound is tested for the classes mentioned in the first column in the table 1.2. In case nitrogen is detected as an extra element in the compound, then the test for the functional groups given in second column of the table 1.2 are performed. If the compound contains halogens as extra elements, then the halogen present is detected and the compounds could be as listed in the third column of table 1.2 given below. We also test the presence of unsaturation in the compound to check whether it contains a double or a triple bond. Table 1.2. Different classes of organic compounds. Look at the screen. I. Compounds containing carbon, hydrogen and oxygen. A. Carbohydrates, Polyhydroxyaldehydes or ketones or compounds which yield these on hydrolysis are called carbohydrates. The simplest type of carbohydrates are monosaccharides and their polymers are called polysaccharides. Carbohydrates containing the aldehydic group are called aldoses while those having a keto group are called ketoses. These may be further designated as either reducing or non-reducing in nature, depending upon whether they reduce Fehling solution, Tollens solution, etc. or not. Simple carbohydrates are water-soluble, give a characteristic smell of burnt sugar on dry heating, give positive steric ammonium nitrate test but do not give 2,4-dinitrophenylhydrazine test. Carbohydrates give the following tests. The melting points of carbohydrates are not of much help in their identification since these generally melt over a range of temperature and often decompose on heating. Molasses test. Molasses test is a general test for identifying carbohydrates. The aqueous solution of the carbohydrate reacts with naphtha which is followed by the addition of concentrated H2SO4 which gives a violet colored ring. Furfuryl or substituted furfuryl is formed from the carbohydrate in presence of conc. H2SO4 which condenses with naphtha to produce a violet ring. The reaction for formation of 5-hydroxymethyl furfuryl from glucose by cyclization and dehydration to produces a violet color with naphtha is shown below. Look at the screen. Procedure. Take 5 mg of the substance in a test tube and add 0.5 ml of water to dissolve it. Add 3 to 4 drops of 10% alcoholic solution of naphtha to the test tube. Then, pour 1 ml of conc. H2SO4 carefully with the help of a dropper along the sides of the test tube so that it forms a layer below the aqueous solution without mixing with it. A violet ring at the junction of the two layers indicates the presence of a carbohydrate. This test can be used for distinguishing the monosaccharides and the disaccharides. Disaccharides also give this test after heating for about 10 minutes when they get partially hydrolyzed to monosaccharides. This test is also a general test for monosaccharides. Look at the screen. Procedure. Heat 1 ml of the aqueous solution of the compound and 1 ml of freshly prepared barford reagent taken in the test tube using a hot water bath for about 2 minutes. The appearance of a red precipitate of Cu2O indicates the presence of a monosaccharide. 3. Test with Fehling solution and Benedict solution. The test with Fehling solution and Benedict solution is used for distinguishing reducing and non-reducing sugars. Aldoses reduce Fehling solution and Benedict solution in an alkaline medium as shown below. Ketoses transform to aldoses in the presence of the base and hence also show these tests. Look at the screen. Aldoses or ketoses in presence of alkali degrade to simple carbonyl compounds which reduce Fehling and Benedict solution. Procedure. Fehling test. Mix 1 ml each of Fehling solution A and B in a test tube and add 1 to 2 ml of the aqueous solution of the compound to it. Heat the test tube for 1 to 2 minutes. The appearance of red precipitate indicates the presence of the reducing sugar. Benedict test. To 1 ml of aqueous solution of the carbohydrate taken in a test tube, add 1 ml of Benedict solutions and heat the test tube. The appearance of red precipitate indicates the presence of the reducing sugar. 4. Bile test. Pentoses and hexoses can be distinguished using this test. A blue-green color is obtained when pentoses react with bile reagent while hexoses give muddy brown to gray color with this reagent. Bile reagent contains oxanol which reacts with furfuryl to give the characteristic color. Procedure. Take 0.5 ml of dilute aqueous solution of the compound in a test tube and add 1 ml of bile reagent to it. Heat the contents of the test tube in a boiling water bath. The appearance of the respective color, characteristic of pentose or a hexose indicates its presence. B. Carboxylic acids. Carboxylic acids behave as an acid by releasing a proton as shown below. Carboxylic acids give the following tests. I. Sodium bicarbonate test. Carboxylic acid react with sodium bicarbonate test solution and brisk effervescence of carbon dioxide evolve in this reaction which are clearly visible. This reaction leads to the formation of the sodium salt of the carboxylic acid as shown below. RCOOH night CO3 arrow RCOONA H2O CO2 up arrow. Procedure. A solution of sodium bicarbonate in water is prepared and a very small amount of the carboxylic acid is added to this solution taken in a test tube. The appearance of effervescence indicates the presence of a carboxyl group in the compound. 2. Fluorescein test. This test is given by dicarboxylic acids such as phthalic and succinic acids. The dicarboxylic acid or its anhydride on heating with resorcinol in the presence of concentrated sulfuric acid gives a yellow-green colored fluorescent dye called fluorescein. Look at the screen. Procedure. Take a dry test tube and add about 50 mg of the given carboxylic acid, 50 mg of resorcinol, and 0.5 ml of concentrated sulfuric acid to it. Heat the test tube gently over the flame of a Bunsen burner for 1 to 2 minutes. Prepare a dilute solution of sodium hydroxide in a beaker and add the contents of the test tube in the alkaline solution in the beaker. The appearance of a bright green color in the solution confirms that the given acid is a dicarboxylic acid. See, aldehydes and ketones. The aldehydes and ketones both contain the carbonyl group and undergo typical reactions such as addition and oxidation due to this group. Several derivatives of ammonia give addition products, as shown below. Look at the screen. Aldehydes and ketones can be distinguished by using some tests in which the aldehydes can be oxidized to carboxylic acids while ketones are not oxidized. These tests are Toland's test, Schiff's test, chromic acid and Felling test. I. Brady's test, reaction with 2,4-dinitrophenylhydrazine, both aldehydes and ketones on reaction with 2,4-dinitrophenylhydrazine give yellow to orange colored solid 2,4-dinitrophenylhydrazinase. Procedure. Dissolve 100 mg of the compound taken in a test tube into 2-3 ml of ethanol. Add 2 ml of 2,4-dinitrophenylhydrazine reagent to the test tube and shake the contents of the test tube. The appearance of a yellow to orange colored precipitate indicates that the given compounds is an aldehyde or a ketone. The yellow color of the precipitate indicates that it is a saturated compound while orange color of the precipitate indicates that it is an unsaturated compound. After confirming the presence of the carbonyl group by the Brady's test, the compound is to be tested for being an aldehyde or a ketone by the following tests. 2. Toland's test. Aldehydes give a silver mirror or dark gray-black precipitate on reaction with Toland's reagent. The aldehyde gets oxidized to the corresponding carboxylic acid and the Toland's reagent is reduced to elemental silver which gets deposited in the form of a silvery mirror on the walls of the test tube. RCOOH2, Ag, NH3, 2O. Procedure. Arcun 4,3NH3H2O2 Ag. Take about 50 mg of the compound in a clean test tube and add 2-3 ml of freshly prepared Toland's reagent. Warm the contents of the test tube on a hot water bath. The appearance of a silver mirror either immediately or on warming indicates the presence of the aldehyde. 3. Schiff's test. Fuchsin hydrochloride has quinonoid structure as shown in the margin. When sulfur dioxide is passed through a solution of fuchsin hydrochloride, the quinonoid structure gets destroyed and a colorless compound is obtained which acts as the Schiff's reagent. The colorless compound being unstable loses sulfurous acid on treatment with the aldehyde and the pink color gets restored. Procedure. About 50 mg to 2-3 drops of the compound is taken in a test tube and 3 to 4 drops of Schiff's reagent are added to the test tube. The appearance of a dark pink or magenta color indicates that the compound is an aldehyde. 4. Felling's test. Aldehydes reduce Cu2 to cut and form a red precipitate of Cu2O while the aldehyde gets oxidized to the carboxylic acid. Felling's solution. I. Preparation of the solution. Look at the screen. 2. Use in oxidation reaction. Procedure. Mix 1 ml each of following solutions, A and B, in a test tube and add 1 to 2 ml of alcoholic solution of the 50 milligrams of the compound to it. Heat the test tube for 1 to 2 minutes. The appearance of red precipitate indicates the presence of the aldehyde. Iodoform test. Carbonyl compounds containing hydrogen on reaction with halogen in the basic medium form iodoform as shown in the reaction given below. Iodoform is a yellow-colored solid. The iodoform reaction indicates the presence of methyl ketones. The mechanism of formation of iodoform is given below. Procedure. Dissolve 100 mg or 3 to 4 drops of the compound into 2-3 ml water taken in a test tube. Then, add 1 ml of 10% sodium hydroxide to the test tube. After that, a saturated aqueous solution of iodine in key is added dropways to the test tube till the dark color of iodine persists. Heat the test tube in a boiling water bath for 2 to 3 minutes. Add a few drops of sodium hydroxide solution to the test tube so that the excess color of the iodine gets removed. The appearance of a yellow precipitate of iodine confirms the presence of CH3 co-group in the compound. D. Phenols. Phenols are weakly acidic in nature and dissolve in dilute sodium hydroxide, but are not soluble in sodium hydrogen carbonate, sodium bicarbonate. However, strongly acidic phenols such as 2,4,6-trinitrophenols are soluble in sodium hydrogen carbonate solution also. Phenols give the following tests. I. Ferric chloride test. Majority of the phenols react with neutral ferric chloride solution and give the dark colored such as blue, green, purple colored complexes. Facial 36C6H5O arrow H3, Fe, OC6H5, 6 purple 3HCl. In the presence of excess facial 3, alpha and beta naphthals undergo oxidative coupling reaction as shown below. Look at the screen. Procedure. Dissolve about 20 mg of compound in 3 to 4 ml of water in a test tube and add a neutral solution of ferric chloride dropways to the test tube. The appearance of red, green, purple or blue color indicates that the compound is a phenolic compound. 2. Lieberman nitroso test. Most phenols give the following reaction on heating with sodium nitrite and concentrated sulfuric acid. Look at the screen. Procedure. Take about 15 mg of compound in a dry test tube and add a few crystals sodium nitrite and about 0.5 ml of concentrated sulfuric acid. Gently heat the contents of the test tube and observe the color. The blue-colored solution so obtained on dilution with water changes to red color solution. The red color of the solution again changes to blue color solution by making it alkaline using potassium sodium hydroxide solution. 3. Phthalate test. Phenols react with phthalic anhydride in the presence of concentrated sulfuric acid to yield condensation products, which give characteristic colors in the basic medium. For example, phenol yields phenolphthalein while resorcinol gives fluorescein, which, respectively, give pink and fluorescent green colors in the alkaline solutions. Procedure. Take 50 mg of the compound in a dry test tube and add 50 mg of phthalic anhydride to the test tube. Then, add 2 to 3 drops of concentrated sulfuric acid to the test tube. Gently heat the contents of the test tube and then allow it to cool. Pour the contents the test tube into a small beaker containing dilute sodium hydroxide solution. The appearance of blue, purple, red, green, etc. colors indicates the presence of a phenol. If large amount of concentrated sodium hydroxide solution added, then the color disappears. 4. Bromine test. Phenols react with bromine to form polybromophenols and hydrogen bromide. Bromine water is an oxidizing, yellow-tone mixture of diatomic bromine, Br2 dissolved in water. Bromine water is also decolorized by some amines, alkenes, alkynes and activated aromatic compounds. Procedure. Dissolve 100 mg of the compound in water or glacial acetic acid. Then, add dropways a dilute solution of bromine in acetic acid, or water. The disappearance of the orange color indicates the presence of a phenol. E. Alcohols. Alcohols give the following tests. I. Ceric ammonium nitrate test. Alcohols react with ceric ammonium nitrate and change its yellow color to red color. Procedure. Dissolve about 50 milligrams of the compound into ml of water taken in a test tube and add a few drops of ceric ammonium nitrate solution to it. Observe the change in color. The change in color from yellow to red indicates that the compound is an alcohol. 2. Test with sodium metal. Alcohols are very weak acids and react with very active metals like sodium. In this reaction, hydrogen gas liberates and metal alkoxides are formed. Procedure. Take a dry test tube and add 1 ml of the compound in it, if the compound is liquid. Otherwise, take a few crystals dissolved in dry benzene, a solvent other than alcohol. Add a very small clean piece of dry sodium to this. If brisk effervescences are observed, the compound is an alcohol. It should be taken care of that the compound and the test tube are absolutely dry. Handle sodium metal very carefully. It should not be discarded in the sink or thrown away in the dustbin. Some other compounds such as acetone may also give positive sodium metal test. 3. Xanthate test. Alcohols react with carbon disulfide in the presence of an alkali and give yellow precipitate of xanthate as given in the following reaction. ROH-KOH arrow KH2O. Procedure. Take a dry test tube and add about 0.2 ml of the compound to it. Then, add 1 pellet of potassium hydroxide to the test tube and warm a little to dissolve the contents. After cooling the contents, wash them with a little amount of ether and decant the ether. Finally, add 3 to 4 drops of carbon disulfide and shake the test tube well. The formation of a yellow colored precipitate indicates that the compound is an alcohol. 4. Lucas test. Lucas test can be used to distinguish between primary, secondary, and tertiary alcohols. The Lucas reagent is anhydrous zinc chloride in concentrated HCl. These alcohols are distinguished according to the time taken by them to form alkyl chlorides. Tertiary alcohols react with the Lucas reagent immediately and the alkyl halide layer separates immediately. The reaction with secondary alcohols occurs within 5 to 10 minutes while primary alcohols do not undergo this reaction. Procedure. Take about 1 ml of the compound in a test tube and add about 2 ml of the Lucas reagent to it. Shake the test tube and note down the time required for the reaction to take place. If a separate layer forms as per the time durations indicated above, the presence of a secondary or a tertiary alcohol is indicated. If no layer separates and the homogeneous solution remains as such, the alcohol is a primary alcohol. V. Iodoform test. Iodoform test is given by those alcohols which contain CH3-CHOR group and can be oxidized to CH3COR during the reaction. A yellow precipitate iodoform is obtained in this test as discussed above for aldehydes as test. V. Procedure. Dissolve 100 milligrams or 3 to 4 drops to 3 ml of the compound in water taken in a test tube. Then, add 1 ml of 10% sodium hydroxide to the test tube. After that, a saturated aqueous solution of iodine in key is added. Drop waste to the test tube till the dark color of iodine persists. Heat the test tube in a boiling water bath for 2 to 3 minutes. Add a few drops of sodium hydroxide solution to the test tube so that the excess color of the iodine gets removed. The appearance of a yellow precipitate of a iodoform confirms the presence of CH3-CHOR group or a group which can be oxidized to CH3COR in the compound. F. Esters. Esters are pleasant-smelling compounds and are extensively used for perfumery purposes. Esters give the following tests. I. Fagel test. Reaction with hydroxylamine. Esters react with hydroxylamine and form hydroxamic acid, which further reacts with FeCl3 and forms a magenta-colored complex. Dissolve about 50 milligrams of the compound in 1 ml of alcohol taken in a test tube and then add 1 ml of 1-MCHL to it. Then, add a few drops of ferric chloride solution to it. If a strong coloration, like red, blue or green appears, then this test cannot be performed for testing the esters. Procedure: take about 50 milligrams of the compound in a test tube and add 1 ml of 0.5 m solution of hydroxylamine hydrochloride and 0.2 ml of 6N sodium hydroxide solution to the test tube. Heat the contents of the test tube to boiling and then let them cool for a while. Add about 1 to 2 ml of alcohol so that the solution becomes clear if it was cloudy in appearance. Then, add 2 to 3 drops of 0.6 m ferric chloride solution. Observe the resulting color. The presence of a magenta color indicates the presence of the ester group in the compound. 2. Hydrolysis. Esters can be hydrolyzed using alkali to the sodium salts of the carboxylic acid and the alcohol. The carboxylic acid and the alcohol formed on hydrolysis as shown above can be individually identified to know the structure of the starting ester. Procedure: take 0.1 g of the compound in a boiling tube and add 2 ml of a dilute solution of sodium hydroxide to it. Add a drop of phenolphthalein and observe the appearance of a pink color. If the pink color fades away, then add some more dilute sodium hydroxide solution so that the pink color persists. Then, boil the contents of the test tube for about 5 minutes. The disappearance of the color indicates the presence of the ester group, G. Hydrocarbons. Hydrocarbons neither contain extra elements nor any functional groups, hence, they do not give any of the tests discussed above. Hydrocarbons give the following tests. I. Test with chloroform. Aromatic hydrocarbons react with chloroform in the presence of anhydrous aluminium chloride to give colored compounds, and this reaction is known as Friedel-Crafts reaction. A colored compound, C6H5, 3C, UlCl4 is formed, and this is taken as a test for aromatic hydrocarbons. Some aromatic hydrocarbons having strongly deactivating groups do not give positive test with chloroform. Procedure: take 100 milligrams of anhydrous UlCl3 in a Pyrex test tube and heat it on the flame. Cool and add 1 to 2 drops or about 20 milligrams of the compound to the test tube. Then, add 2 to 3 drops of chloroform. The presence of an aromatic compound is indicated by the appearance of the following characteristic colors: benzene and its homologues, orange to red, aryl halide, ARX, X is equal to Cl, Br, I, orange to red, naphthalene, blue, biphenyl purple. 2. Reaction with fuming sulfuric acid. Aromatic hydrocarbons are soluble in fuming sulfuric acid and can be differentiated from saturated aliphatic compounds by dissolving the compound in fuming sulfuric acid. Procedure: the solubility of the given compound can be checked by taking its 0.2 g in a test tube and shaking it with 2 ml of 20% of fuming sulfuric acid. The aromatic hydrocarbons are soluble while the saturated, aliphatic and cyclic compounds are not soluble in fuming sulfuric acid. 2. Compound containing nitrogen. Common nitrogen-containing compounds include nitro compounds, primary, secondary and tertiary amines, and amides, substituted amide also. Here, we will discuss the tests for each of these classes of compounds. A. Nitro compounds. The nitro compounds are usually yellowish in color and give different reduction products depending upon the reducing agent used. Thus, they act as oxidizing agents. The following tests can be used to check the presence of nitro group in a compound. I. Mulliken-Barker test. This test involves the reduction of a nitro group to NO group, which further reacts with Tollens reagent and gets oxidized to the nitroso compound. The silver so obtained as reduction product from the toluenes reagent appears as a gray precipitate. Procedure: take 100 milligrams of the compound in a test tube and add 1 ml of dilute alcohol. Then, add 100 milligrams of zinc dust and 1 ml of a solution of ammonium chloride 0.5 g to the test tube. Boil the contents of the test tube for 2 to 3 minutes and filter them in a clean test tube. Then, add 1 ml of freshly prepared toluenes reagent to the test tube. The appearance of a gray precipitate in the test tube which slowly turns black indicates the presence of a nitro group. 2. Reduction. Aromatic nitro compounds may be reduced to amino compounds with tin. An HCl dye test can then be performed on the reduced product. The test is applicable only if the original compound does not give the azo dye test. Procedure: reflux 0.5 g of the organic compound into 2-3 ml alcohol with 2-3 pieces, tin and 5 ml conc. Hydrochloric acid for about 15 minutes. Extract the amino compounds so obtained with ether. Remove ether using a hot water bath. You can perform the azo dye test with the amine. The details of the same are given below in tests for amines on page number 34. 3. Ferrous hydroxide test. Nitro compounds being oxidizing in nature can oxidize ferrous hydroxide to ferric hydroxide. Procedure: take about 20 milligrams of the nitro compound, 1 to 2 drops, if the compound is liquid, in a test tube and add 2 ml of 5% freshly prepared ferrous ammonium sulfate solution to the test tube. Then add 1 or 2 drops of 3,M sulfuric acid to the test tube. Finally, add 1 ml of 2M potassium hydroxide solution in methanol to the test tube. Stopper the test tube and shake the contents well. The appearance of a brown precipitate indicates the presence of the nitro group in the compound. B. Amines. Amines can be primary, secondary or tertiary. Amines are basic in nature and dissolve in dilute hydrochloric acid when solubility test is performed on the compound. Primary, secondary or tertiary amines can be differentiated from each other by the following tests. I. Hinsberg test. This test uses 5% dilute solution of benzenesulfonyl chloride in sodium hydroxide as the reagent. The benzenesulfonyl derivative of the amine is thus obtained in case of primary and secondary amines. Procedure: take 0.5 g of the compound and add 1 ml of 5% sodium hydroxide solution and 1 ml of benzenesulfonyl chloride in a test tube very carefully. Stopper the test tube and shake the contents of the test tube for about 5 minutes. Observe the products so obtained. Dilute the contents of the test tube with water. If the precipitate dissolves, then it indicates the presence of a primary amine, but if the precipitate does not dissolve, secondary amine is indicated. 2. Nitrous acid test. The primary, secondary and tertiary amines can also be identified using nitrous acid. Primary aromatic amines form diazonium salts with nitrous acids. Since the diazonium salts decompose at higher temperatures, this reaction is carried out between 0 to 5 degrees centigrade. The diazonium salts so obtained from the primary aromatic amine then can be coupled with phenols such as beta-naphthyl to leave orange-red colored azo dyes as given in A. Below. Aliphatic primary amines react with nitrous acids and form alcohol and nitrogen gas, RNH2, HNO2, ROHN2H2O. Both aliphatic and aromatic primary amines show carbylamine test as given in B. The secondary aliphatic and aromatic amines on reaction with nitrous acid form N-nitroso derivatives which are insoluble liquids and hence separate from the reaction mixture as oily layer. The tertiary aromatic amines form para-nitroso derivatives if the para position is free. The para-nitroso derivative separates as an orange-colored solid in the form of its hydrochloride. This orange-colored Derivative turns to green solid on treatment with sodium hydroxide solution. The tertiary aliphatic amine forms a salt with nitrous acid. Procedure: take 2.0 ml of conc. Hydrochloric acid and 2.0 ml of water in a test tube, and dissolve 0.1 g of the compound in it. Cool the contents of the test tube to 0-5 oC by keeping it in an ice bath. Take 0.1 g of sodium nitrite in a test tube and add 2.0 ml of water to it and cool the contents of the test tube to 0-5 degrees C by keeping it in an ice bath. Then, dropways add sodium nitrite solution to the test tube containing the organic compound. Shake the contents of the test tube so that they are completely mixed up. Observe if the nitrogen gas evolves. In that case, the amine is primary, aliphatic amine. In that case, the primary amine is to be tested for the carbylamine test as given in B, shown below. If the solution remains clear, then the compound may be an aromatic amine which can be confirmed by using the azo dye test. In case an oily product separates, then the amine is a secondary amine which can be confirmed by the Lieberman nitroso test given in C, below. The tertiary aromatic amine is indicated by the deep orange-red colored solid which can be confirmed by neutralization to a green solid. A. Coupling of the diazonium salt. The diazonium salt obtained by diazotization of primary aromatic amines can be coupled with beta-naphtha or other phenols to give red-colored azo dye which separates out. Procedure: take the diazonium salt obtained as explained above in 2 by mixing the cold solutions of organic compound in dilute hydrochloric acid and sodium nitrite solution to the diazonium salt solution. Add a solution of beta-naphtha in sodium hydroxide, 0.1 g of beta-naphtha dissolved in 5 ml of 10% NaOH, dropways. Shake the mixture well. The formation of an orange-red dye confirms the presence of an aromatic primary amine. B. Carbylamine test. Primary amines, both aliphatic and aromatic, produce carbylamine or isocyanide on heating with chloroform in the presence of alkali. Procedure: take 5 mg of the organic compound in a dry test tube and add 2 to 3 drops of chloroform and about 1 ml of alcoholic potassium hydroxide solution. Carefully warm the contents of the test tube in a fume hood. Keep the mouth of the test tube away from you and do not smell the gas evolved on heating. A foul smell of isocyanide formed confirms the presence of a primary amine. To dispose of the isocyanides so formed, add conc. HCl to the test tube and leave for about 10 minutes without disturbing. Then, discard the contents of the test tube to the sink and flush with water. The secondary amine on reaction with HNO2 forms N-nitrosamine. The nitrous acid HNO2 is formed by the reaction of sodium nitrite with concentrated sulfuric acid. C. Lieberman nitroso test. In this test, the N-nitrosamine formed by the secondary amine is warmed with phenol and conc. Sulfuric acid. The sulfuric acid and a nitrosamine react and nitrous acid is liberated which then reacts with phenol to form paranitrosophenol. The paranitrosophenol then combines with one more molecule of phenol to give the red-colored indophenol. The indophenol yields a blue color on treatment with alkali by the formation of indophenol. Anion. The sequence of reactions occurring is shown below. Look at the screen. Procedure: extract the oily layer formed by the reaction of the secondary amine with nitrous acid with ether. Wash the ether layer with dilute urea solution and dry it over anhydrous calcium chloride. After filtering the solid CaCl2 and evaporating the ether on a water bath carefully, the residue so obtained is heated with phenol. It is then cooled and then a few drops of conc, sulfuric acid are added. The red indophenol formed turns blue on treatment with dilute alkali. C. Amides. Amides can be aliphatic or aromatic amines. Further, they can be primary, amides or substituted amines. Primary amides can be represented as arcon-2 or ARCONH2 depending upon whether it is aliphatic or aromatic amide. However, aliphatic substituted amides can be represented as arconha and arcon. The aromatic substituted amides can be represented as ARCONHR and ARCONR. Amides can be hydrolysed either by alkalis or acids. We will now describe the following tests for amides. Alkaline hydrolysis. Amides on hydrolysis with sodium hydroxide yield ammonia. Procedure. Take 0.2 g of the compound in a test tube and add 5 ml of 15% NaOH solution to it. Gently boil the contents of the test tube using a flame. The evolution of ammonia indicates the compound to be an amide or an imide. 2. Biuret test. Urea on heating gives biuret which on treatment with Cu2 ions in the presence of a base give a purple-colored complex. Procedure. Take 0.1 g of the compound in a dry test tube and heat till the compound melts and solidifies and the evolution of ammonia ceases. Dissolve the solid after cooling in dilute NaOH solution and add 1 to 2 drops of copper sulfate solution to it. The formation of purple of violet color indicates the presence of urea in the alkaline hydrolysis of the amide. Sodium salt of the carboxylic acid is obtained along with the evolution of ammonia as shown in the above reaction. The carboxylic acid can then be liberated from its sodium salt by acidification. The carboxylic acid so obtained can be then be identified by performing the test for carboxylic acid as given in B. 3. Compound containing halogens. Out of the alkyl, vinyl and aryl halides, only alkyl halides undergo substitution reactions by a nucleophile because alkyl halides are more reactive. Some tests for halides are given below. Alcoholic silver nitrate test. The bromides and iodides are more reactive and react readily than the chlorides. The primary halides are least reactive, but the tertiary alkyl halides and benzyl halides are the most reactive ones. The aryl halides do not show any reaction with alcoholic silver nitrate under these conditions. Procedure. 1 drop of compound or 100 mg of the compound is added to 1 ml of 0.1 m alcoholic solution of silver nitrate. Warm the mixture a little on a water bath. The formation of a precipitate indicates the compound to be an alkyl halide while the clear solution indicates the halide to be an aryl or a vinyl halide. 2. Reaction with sodium iodide in acetone, Finkelstein reaction. Alkyl chlorides and bromides on treatment with a solution of sodium iodide in acetone yield a white precipitate or a pale yellow precipitate, respectively according to the following reactions. Look at the screen. Procedure. Take 1 to 2 drops of the compound, if liquid or about 50 mg of the compound in a test tube and add 1 ml of 15% solution of sodium iodide in acetone to it. Shake the contents well and allow the test tube to rest at the room temperature for 4 to 5 minutes. Watch if any precipitate appears in the test tube. Otherwise, warm the contents of the test tube for 3 to 5 minutes. The formation of a precipitate indicates the compound to be an alkyl chloride or an alkyl bromide. The tertiary alkyl chlorides and bromides react the fastest as compared to the other halides. The aryl chlorides and bromides do not form a precipitate in this reaction. 4. Tests for unsaturation. A. Alkenes and alkynes. Test for unsaturation using bromine in carbon tetrachloride solution. The presence of a multiple bond, i.e. double bond in a compound can be detected using bromine in CCl4. In case the double bond is present, the dark yellow color of the bromine gets discharged and we get a colorless solution. However, the presence of an electron withdrawing group on the carbon atom of an ethylenic bond causes the addition to be slow, and in extreme cases, such compounds may not react with bromine at room temperature. For example, C6H5CH is equal to 2 reacts slowly with bromine and C6H5 to C is equal to C. C6H5 2 does not react with bromine in carbon tetrachloride. A positive test for unsaturation is one in which the color of the bromine is discharged without the evolution of hydrogen bromide. Discharge of the color of bromine accompanied by evolution of hydrogen bromide indicates that substitution has occurred. Many aromatic compounds, which have electron-donating groups present on the ring, undergo this type of reaction. Some typical compounds are phenols and amines. HBr is evolved in a substitution reaction and no HBr is obtained if addition of bromine takes place. Evolution of HBr is observed only if carbon tetrachloride has been used as a solvent. If the reaction is carried out with Br to water instead, HBr cannot be easily detected as it is soluble in water. The rate of bromination reaction is greatly enhanced in polar solvents like water, acetic acid, etc. Procedure: dissolve 0.1 g or 0.1 ml of the organic compound into ml carbon tetrachloride and add a 5% solution of bromine in carbon tetrachloride to it dropwise with shaking. The discharge of color of bromine without evolution of HBr shows the presence of unsaturation in the compound. Note 1. Dense white fumes are produced when a glass rod dipped in ammonia solution is brought near the mouth of the test tube if HBr is evolved in the reaction. 2. Bare test. Reaction with potassium permanganate. Compounds containing ethylenic and acetylenic linkages decolorize a solution of potassium permanganate, i.e. the purple color of KMNO4, may change to reddish brown indicating the presence of unsaturation. Olefins are oxidized to glycols. Permanganate solution even if no olefinic or acetylenic bonds are present. Example, some aldehydes, phenols, formic acid and its esters, thiols, thioesters, etc. So the decolorization of KMNO4 solution is either due to unsaturation or oxidation of easily oxidizable groups. Procedure: dissolve 0.1 g or 0.1 ml of the organic compound into ml water or acetone if the compound is insoluble in water. Add 2% aqueous potassium permanganate solution dropwise with shaking. Decolorization of a few drops of potassium permanganate solution is a positive test. Note: use a freshly prepared solution of the compound in acetone for the test. Also carry out a blank test for comparison. 1.4.6 Preparation of derivatives. According to the functional groups identified in Step 5 in Sec 1.3 above, the crystalline derivatives for each of the identified compounds are prepared and their melting points are compared with the melting point of the known compound derivative given in the literature. This will lead to the confirmation of the identified compound. Normally, 1 or 2 derivatives are prepared which are simple and could be easily prepared in good yield. The derivative is purified by crystallization and its melting point is compared with literature melting point. Usually, the following derivatives, as given in Table 1.3, are prepared for the various classes of the compounds as identified in the Step 5 above. Appendix I, data tables of organic compounds and their derivatives. Table 1.3, derivatives usually prepared or different classes or organic compounds. Look at the screen. Procedures for preparation of derivatives. 1. Carbohydrates. The following 2 derivatives are prepared for the carbohydrates. I. Acetate. The acetylation of glucose can yield either pentacetate or beta-pentacetate. The procedures for the formation of the same are given below. A. Preparation of pentacetate. I. Reflux a mixture of 10 ml acetic anhydride, 0.5 g fused zinc chloride, and 1.0 g carbohydrate in a water bath for 1 hour. The carbohydrate should preferably be added in small lots during refluxing. 2. Take a beaker containing 100 ml ice-cold water and pour the reaction mixture into it. Stir well so that acetic anhydride Decomposes. 3. Filter the product formed. 4. Recrystallize the product from methanol or ethanol. B. Preparation of pentacetate. I. Take 1 g of carbohydrate, 1 g of sodium acetate, and 7 ml of acetic anhydride in a dry round bottom flask or a boiling tube. 2. Reflux the contents on a water bath for about 1 hour after fitting a condenser on it. 3. Pour the reaction mixture over 50 ml ice-cold water taken in a beaker and stir vigorously. Excess acetic anhydride will be decomposed. 4. Filter the solid so-octane and wash it thoroughly with cold water. We recrystallize from ethanol. 2. Oxazone. I. Dissolve 1 g carbohydrate, 2 g phenyl hydrazine hydrochloride and 3 g sodium acetate in 15 ml water taken in conical flask. 2. Loosely cork the flask and heat it on a boiling water bath for about 30 minutes. A yellow-colored oxazone would appear. Note the time for its appearance. 3. Filter the oxazone and recrystallize from alcohol. 2. Carboxylic acids, amides, analydes and petoludides are prepared as derivatives for identification of carboxylic acids. The carboxylic acid is first converted to its acid chloride, which is then treated with ammonia, aniline or petoluidine to yield the amide, analyde and petoludide, respectively. Acid chlorides can be prepared by using thionyl chloride or PCl5 or PCl3 chloride. The acid chloride can be prepared from the carboxylic acid or its salt, and thionyl chloride, RCOOH SOCl2. Arrow RCOCl-SO2 HCl, RCONA SOCl2 arrow RCOCl-SO2 NaCl. Preparation of acid chloride. I. Take 1 g carboxylic acid and 2 cubic centimeters thionyl chloride in a small dry round bottom flask. 2. Attach a reflux condenser and reflux the mixture for about 30 minutes. Precipitate of acid chloride will appear at the bottom of the flask. Procedure for preparing amide and analyde derivatives. The methods of preparation for amides and analydes derivatives are as given below. I. Amide. The carboxylic acid chloride prepared above can be converted to the amide. I. Take the acid chloride in a dry china dish and treat it with excess of concentrated ammonia having specific gravity 0.88. 2. Warm the contents for a few minutes and then let it cool. 3. The solid crude amide should separate out. Recrystallize from water or dilute ethanol. 2. Analyde. The carboxylic acid chloride prepared above can be converted to the analyde. I. Take about 1 g of the acid chloride and add 1 to 2 ml of a solution of aniline in benzene to it. 2. Warm the contents on a water bath for about 5 to 10 minutes and notice if any solid separates out. 3. If no solid separates, then wash the benzene layer with water, dilute HCl, dilute NaOH, and then with distilled water. 4. Dry the contents over anhydrous calcium chloride or sodium sulfate. We carefully remove the benzene by distillation. 6. Recrystallize the solid so-octane from ethanol. 3. S-benzylesethuronium salt. The carboxylic acids and their sodium salts can be converted to their S-benzylesethuronium salts on treatment with S-benzylesethuronium chloride. I. Take 0.5 g of the carboxylic acid in 5 ml of water or alcohol and add 1 to 2 drops of phenolphthalein to it. 2. Add dilute sodium hydroxide solution to neutralize it. Then, add a few drops of dilute HCl to get a light pink-colored solution. 3. Dissolve 2 g of S-benzylesethuronium chloride in 7 to 8 ml of water and add it to the pink-colored solution obtained in 2 above. 4. Cool the contents and filter the solid so obtained. We recrystallize the analyde from ethanol. 3. Aldehydes and ketones. I. 2,4-dinitrophenylhydrazine. Aldehydes and ketones both give 2,4-dinitrophenylhydrazine derivatives. On reaction with 2,4-dinitrophenylhydrazine, I. Dissolve 0.5 g of aldehyde or ketone taken in a test tube 1 ml of ethanol. 2. Add to 3 cubic centimeters of the 2,4-dinitrophenylhydrazine reagent. 3. Heat the contents on water bath for about 10 to 15 minutes. 4. Let it cool so that an orange-red solid separates out. We filter the solid so obtained and wash it with aqueous methanol. 6. Recrystallize the solid from ethanol or ethyl acetate. 2. Semicarbazone. Aldehydes and ketones both give 2,4-dinitrophenylide resin derivatives on reaction with semicarbazide hydrochloride as shown below. I. Dissolve 0.5 g semicarbazide hydrochloride and 0.8 g sodium acetate into 2-3 ml of water 5 cubic centimeters of water in a test tube. 2. Add a solution of 0.5 g of the carbonyl compound alcohol or water. Drop waste to the test tube and keep shaking. 3. If no solid separates, heat the mixture for 10 to 20 minutes on a water bath. 4. Cool the test tube in ice and filter the solid obtained. We recrystallize the solid from ethanol or methanol. 3. Oxime, aldehydes and ketones both give oxime derivatives on reaction with hydroxylamine hydrochloride. I. In a test tube, take 0.5 g hydroxylamine hydrochloride, 0.5 g sodium acetate and dissolve them into 2-3 ml of water. 2. Add 0.5 g of the aldehyde or ketone into 2-3 ml of water and add a few drops of ethanol if a clear solution was not obtained by addition of water. 3. Add the solution of the carbonyl compound to the test tube. Reflux for 10 minutes. 4. Cool the contents and filter the solid so obtained. We recrystallize the solid from ethanol. 4. Iodoform. Iodoform can be prepared for aldehydes and ketones and containing CH3CO group or CH3CHO group. I. Dissolve about 200 mg of the compound into 2-3 ml of water, boiling tube. 2. Add 1 ml of 10% sodium hydroxide solution. Then, add saturated, aqueous solution of iodine in potassium iodide and keep shaking till the brown color of the iodine persists. 3. Heat the solution on a water bath or 2 to 3 minutes. 4. Add a few drops of a NaOH solution to remove the color of excess iodine. The light yellow colored solid obtained is iodoform. 6. Filter and recrystallize it from ethanol. 4. Phenols. Benzoate. Take benzoates can be prepared as derivatives for phenols. Take 1 g of phenol on a 100 ml conical flask and a 20 ml of 10% NaOH solution to it. 2. Slowly add 2 ml of benzoyl chloride in small quantities while shaking and keeping the flask closed by a cork. 3. Cool the flask and its contents. 4. Filter the solid so obtained and wash it with water. We recrystallize the benzoate derivative using ethanol. 2. Bromoderivative. Many phenols also form crystalline bromo derivatives. Take 0.5 g of phenol and add a solution of bromine in glacial acetic acid slowly till the color of bromine persists on shaking. 2. Let it cool for 15 minutes and for the contents into the cold water. 3. Filter the solid so obtained and wash the solid with water. 4. Recrystallize from alcohol. 3,5-dinitrobenzoate. Similar to benzoates, 3,5-dinitrobenzoate can also be prepared as derivatives of phenols. Many phenols also form crystalline bromo derivatives. Take 1 g phenol in a 50 ml flask and add 0.5 g of 3,5-dinitrobenzoyl chloride to it. 2. Heat the contents and then cool in ice-cold water. 3. Wash the contents with sodium bicarbonate solution and then by water. 4. Recrystallize the product from alcohol. 5. Alcohols. 3,5-dinitrobenzoate. Similar to phenols, alcohols can form 3,5-dinitrobenzoate derivatives. Dissolve the 2 ml of the given alcohol and add 2 g of 3,5-dinitrobenzoyl chloride to it taken in a 100 ml round-bottomed flask. 2. Reflux for about 10 to 15 minutes and pour the contents into 100 ml ice-cold water. 3. Filter the solid so obtained and wash it with sodium bicarbonate solution so that no acid remains. 4. Wash the solid with water and recrystallize the bromoderivative from alcohol. In dry 5 ml pyridine and add 1 to G3. 5 dinitrobenzol chloride in a 100 ml round-bottomed flask. Reflux the reaction mixture for about 30 minutes and pour it into 40 cubic centimeters of hydrochloride acid. Separate the solid or oily product and stir with 15 cubic centimeters sodium carbonate solution 1 m to remove any 3,5-dinitrobenzoic acid formed. Filter the solid and recrystallized from petroleum 60 to 80 degrees centigrade ethanol or aqueous ethanol. 2. Benzoate, similar to 3,5-dinitrobenzoate derivatives alcohols also form benzoates. The procedure used is same as described above for 3,5-dinitrobenzoates. 3. Oxidation to aldehyde ketone carboxylic acid. Primary alcohols can be oxidized to the corresponding carboxylic acids. I. Take about 1 g of the alcohol in a round bottom flask and add 30 ml of water and 1 g sodium carbonate to it. 2. Then, add 4 g potassium permanganate in small lots with constant shaking. 3. Reflux the contents for about half an hour. 4. Let the reaction mixture cool and then add dilute sulfuric acid to it. To acidify it, we add a solution of sodium sulfide to dissolve the precipitated manganese dioxide. 6. Filter the carboxylic acid and recrystallize it from hot water. 6. Esters. Esters on hydrolysis with aqueous alkali form sodium salt of the carboxylic acid and alcohol or a phenol. 1 ml of the ester can be refluxed with 15 ml of 15% sodium hydroxide solution in a round bottom flask for about 1 hour. 2. The contents are then allowed to cool and a small portion of this is diluted with water and distilled. 3. The distillate is then checked for the alcohol and iodoform test is also performed in the distillate for the alcohol. 4. The alcohol is then characterized after isolating it by preparing its 3,5-dinitrobenzoate 3,5-dinitrobenzoate of alcohol part 2 acid obtained after saponification. The remaining portion from step 2 after removing the alcohol contains the sodium salt of the carboxylic acid. It is then isolated as discussed below. The sodium salt of the carboxylic acid is acidified using dilute HCl or dilute sulfuric acid. 2. Filter if a solid is obtained. Otherwise, the contents are then to be extracted with ether. 3. Carefully remove the ether to get the carboxylic acid. 4. Identify the carboxylic acid as discussed above in point 2 on page 19. 7. Hydrocarbons, aromatic, normally, picrates or nitro derivatives are prepared for hydrocarbons. Picrate, polynuclear hydrocarbon can be characterized by picrate formation. Dissolve the 0.5 g of the hydrocarbon compound in 10 ml ethanol and add 5 ml of saturated ethanolic solution of picric acid to it. 2. Heat the reaction mixture on water bath for about 3 minutes and then let it cool. 3. Filter the solid product so obtained. 4. Recrystallize the picrate from ethanol. 2. Nitro derivative. Carefully add 5 ml each of conc. Sulfuric acid and conc. Nitric acid. In a round bottom flask. 2. Add 1 ml or 1 g of the compound to the flask. 3. Fit a water condenser and reflux for about 20 minutes on a water bath or over a burner using wire gauze. 4. Allow the contents to cool and then pour them over ice-cold water. We filter the solid so obtained. 6. Finally, recrystallize from dilute alcohol. 8. Nitro compounds. Mononitro compounds can either be further nitrated or converted to the amino derivative by the reduction of the nitro group. Preparation of dinitro derivative. Carefully add 5 ml each of conc. Sulfuric acid and fuming nitric acid in a round bottom flask. 2. Add 1 ml or 1 g of the compound to the flask. 3. Fit a water condenser and reflux for about 20 minutes on a water bath or over a burner using wire gauze. 4. Allow the contents to cool and then pour them over ice-cold water. We filter the solid so obtained. 6. Finally, Recrystallize the product from dilute alcohol. 2. Reduction to an amine followed by diazotization. I. Take about 1.0 g of the compound and 3.0 g of granulated tin in a round bottom flask fitted with a reflux condenser. 2. Slowly add 10.0 ml of concentrated hydrochloride acid in small portions. 3. Shake the contents and then reflux for 15 minutes. 4. Cool the mixture and then add 30% NaOH solution to it. We extract the amine so formed with ether. Then carefully remove the ether and cool it in ice bath 5 degrees Celsius. 6. Then add 5 to 6 drops of conc. HCl and 1.0 ml of 5% aqueous sodium nitrite. 7. To this, add 2 ml of 5% solution of 2-naphthalene to M sodium hydroxide and see what happens. If an aromatic nitro compound was present, then red to orange precipitate will form. However, if no colored precipitate forms, then the presence of an aliphatic nitro compound is indicated. IGNOU. White to yellow precipitate formed, if any. 9. Amines. For primary and secondary amines, benzoate and toluene 4-sulfonate derivatives are prepared. The acetyl derivative is also prepared for many amines. Tertiary amines, however, do not exhibit these reactions. For tertiary amines, picrates and methiodes are prepared as derivatives. The procedures for various derivatives are as follows. I. Benzoate, Scotton-Bowman method. I. Take 1 g of compound on a boiling tube and add 3 ml of 2M NaOH solution to it. 2. Slowly add 2 ml of benzol chloride in small quantities while shaking and keeping the boiling tube closed by a cork. 3. Shake vigorously until a solid separates out. 4. Cool the contents of the boiling tube. We filter the solid so obtained and wash it with water. 6. Recrystallize the benzoate derivative using ethanol. 2. Toluene 4-sulfonate. For preparing toluene 4-sulfonate, use toluene 4-sulfonyl chloride instead of benzol chloride. 3. Acetyl derivative. Primary and secondary amines are best acetylated with acetic anhydride. I. Take 0.5 g amine, 1 ml acetic acid and 1 ml acetic anhydride in a conical flask. 2. Heat the contents for about 15 minutes. 3. Cool and pour the contents into ice water. 4. Filter the solid and crystallize from water or aqueous ethanol. 4. Bromo derivatives of amines. I. Take 0.5 g of aniline and add a solution of bromine in glacial acetic acid slowly till the color of bromine persists on shaking. 2. Let it cool for 15 minutes and for the contents into the cold water. 3. Filter the solid so obtained and wash the solid with water. 4. Recrystallize from alcohol. We. Picrates. I. Dissolve the 0.5 g amine into 2-3 ml ethanol in a boiling tube and then add 5 ml of saturated ethanolic solution of picric acid. 2. Heat the contents on a water bath for 3 to 5 minutes and allow it to cool. 3. Filter the solid product formed. 4. Recrystallize the product from ethanol. 6. P-nitroso derivative. I. Dissolve the 1.0 g tertiary amine in 10 ml of dilute hydrochloric acid. 1. 2. Cool the solution to 0-5 OC and slowly add a cold solution of 0.7 g sodium nitrite in water 4 ml with stirring. You should maintain the temperature below 5 OC during the addition. 3. Filter the precipitated hydrochloride of P-nitroso derivative and wash it with dilute hydrochloric acid. 4. Dissolve the solid so obtain in a minimum amount of water and make the solution alkaline by adding dilute sodium hydroxide to it. We extract the P-nitroso derivative with ether. 6. Carefully evaporate ether and recrystallize the product from light petrol or benzene. 7. Methodides. I. Take 0.5 g amine and 1 ml of methyl iodide in a boiling tube and gently warm the mixture on a water bath 0.5 g cm3 for several minutes. 2. After about 10 minutes, take the boiling tube out of the water bath. and cool it in ice. 3. A crystalline solid will appear. 4. Filter the product and recrystallize it from ethanol or methanol or ethyl acetate. 9. Amide, alkaline hydrolysis. You know that amides on hydrolysis with sodium hydroxide yield ammonia. By the hydrolysis of the amide as shown above, the sodium salt of the carboxylic acid so obtained is converted to the carboxylic by the following steps. I take 1 g of the amide and 10 ml of 10% nauate solution in a round, bottomed flask. 2. Reflux the contents of the flask for about 30 minutes. 3. Cool the contents and acidify with dilute sulfuric acid. 4. Filter the carboxylic acid so obtained and recrystallized it from ethanol. The derivatives of the carboxylic acid so obtained can then be prepared. 10. Alkyl halide. The following derivatives can be prepared for alkyl halides. Alkyl beta-naphthyl ether. The alkyl halide is reacted with sodium or potassium salt of beta-naphthyl. Dissolve 1 gram of beta-naphthyl in 8 ml of alcoholic solution of sodium hydroxide 0.3 g taken in a round bottomed flask. 2. Then add 1 g of alkyl halide to the flask and reflux for about half an hour. 3. Let the contents of the flask cool and filter the product so formed. 4. Recrystallize the alkyl beta-naphthyl ether from alcohol. 2. Pictrate of alkyl beta-naphthyl ether. The picrate is prepared if alkyl beta-naphthyl ether formed above is not a solid and is not separable. The alkyl beta-naphthyl ether is dissolved in minimum amount of hot alcohol. 2. Then the required amount of picric acid solution is added and the contents are heated to get the clear solution. 3. The contents are then cooled to get the picrate, which is finally crystallized from alcohol. 3. Nitro derivative. The nitration of the alkyl halides can be done by using the same procedure as done earlier for hydrocarbons above in point 7. 11. Aryl halide. Similar to alkyl halides, nitro derivatives can prepared for aryl halides. 1.5 Summary. In this unit, you learnt about the following aspects of separation of components of a mixture of two organic compounds and their identification. In the beginning, we explained the general principle of separation of organic compounds from their mixture, then the separation of components of the mixture after ascertaining their nature as acidic, basic or neutral was explained in detail. The characteristics, tests for different functional groups present in the separated compounds were discussed. Thus, by performing the characteristic tests, the separated compounds could be identified using their physical constants and preparing their suitable derivatives. The physical constants such as melting point and boiling point of the compound and those of the derivatives prepared are confirmed from their literature values to finally identify the organic compounds present in the mixture. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.